In this video, we're going to look at solving absolute value inequalities. We're going to initially start by remembering what we learned with absolute value equations. So let's say we have the absolute value of x equal to 6. Well, what that means, just conceptually speaking, is that x could be 6 or negative 6. Because if we plug a 6 in for x, the absolute value of 6 is 6. And if we plug a negative 6 in for x, well, the absolute value of negative 6 is also 6. So that gives us a solution to the equation. Now, once these got more complicated, we would create two cases where we split this equation into two equations. And we would do something like that. And then when the more complicated ones, this wouldn't be just an x, and so then we would use our solving techniques to take it down from there. This one's simple enough that we can handle it conceptually. So we're going to move to the absolute value inequalities now, but there's some complexities involved with that we don't have to deal with in equations. First of all is the sign. With an equal sign, as an equal sign gets an equal sign, but with inequalities we have our less thans, and less than and equal to's, are greater thans, and then their partner greater than or equal to. And so that adds a complexity because what you do with one is going to be different than what you do with the other. The other issue is when we split equations, the conjunction on the two equations we created was always an or. And because it's always an or, we don't really have to consider what's going to happen because it's always kind of the same thing. Or is the thing that unites all possibilities, and so we just keep all our solutions. When we break our absolute value inequalities into two equations, sometimes that'll be an or and sometimes that'll be an and so we'll have to think through that process, which again just adds another complexity to the issue. But essentially, as a spoiler, when we deal with absolute value inequalities, it's going to break apart into a compound inequality that we then have to solve. Let's start out with a very straightforward example so we can see what's happening with the inequality symbol as well as the and or issue. Alright, let's consider the absolute value inequality. The absolute value of x is less than 3. And let's think about what this is actually saying. So the absolute value of something is its distance from 0. So to say the absolute value of x is less than 3 is saying that its distance from 0 is less than 3. So conceptually speaking, this would be what we're dealing with, is all the numbers that are a distance from 3 units, within a distance of 3 units from 0. So, and that's going to be in the positive and negative case, because those are both a distance of 3 units from 0. And so then from there we could bust out the integral notation, but what we're wanting to do is use this very simple case to help guide our thinking on what to do in more complicated cases. So now, even though we can conceptually get to an understanding of what our solution set looks like, I'm going to kind of break it out in more detail so we can use what we're seeing here for more complicated inequalities. Okay, let's start. I'm going to put a little squiggly here to say now we're going to actually work on solving this guy. And I'm going to move the, I wasn't thinking ahead enough. I'm going to move my graph over as well. Alright, so now I'm going to treat this just like it's an equation, so to speak, for starters, but we're going to have to kind of finesse it a little bit. So if this were an equation, we would say that x is less than 3, and then we would have another version like this. You might want to hold off on writing any of this down because I'm just developing stuff and I'm going to be erasing and changing and altering what I'm writing. And here's the idea though. So this hopefully makes sense, and this is what we call the positive case. This is the negative case. In general, positive cases are straightforward and do what we expect. The negative case here we kind of have to think about. So if we go back to our graph up here to say that x is less than 3, that kind of makes sense because on the 3 side of the graph we're going smaller than that, right? Now it would keep going forever if it was just strictly less than 3. The one that doesn't work so well is if we say that x is also less than -3. That's not really what that means when we talk about x being within 3 units of of 3. So if it's within 3 units of -3, the negative side should reflect back the other way. In other words, that's one good argument for this actually needing to be a greater than sign, okay? But I'm going to give you another argument that's more algebraic that is sometimes more satisfying for students. For this second argument, you have to reflect back to the idea that when we talk about the absolute value of, let's say, a 6, and we split that, we would say x is equal to 6 or x is equal to a -6. We're really not making, and this seems subtle to students, but it's a big deal. We're not making this 6 into a positive and -6. That's not what we're saying. We are actually working with the left side of the equation. And we're saying if we're interested in the absolute value of x, then that x, before it was absoluted, could have been a 6 or it could have been a -6. That's true of any absolute value, whether or not it's in an equation. For the result of it, and this is the result of it, to be a positive 6, it had to start as a 6 or a -6. So what I'm trying to emphasize there is when we split these equations, we're not making the right side positive and negative. What we're really doing is saying what's inside the absolute value has to be positive or negative. Like, we have to consider both cases. With that in mind, another way to emphasize this is instead of having x equal to 3 or x equal to -3, we could write x equal to 3 or -x equals to 3. So the expression that's inside the absolute value is positive or negative. There's a couple reasons why we don't usually write it this way, but the notion there is then we would divide by the negative and we would get back to where we were going straight to in the first place. It's a little complicated because technically it's not a negative x. It's x is a positive number or x is a negative number. But this kind of gives an algebraic explanation for reassociating that sign or emphasizing the sign issues. We do something similar when we work with radicals, where we emphasize the signs separate from the value of the variable. Okay, so now with this thinking, using this idea of making what's inside the absolute value a positive case and a negative case, let's apply this to the inequality that we're working with. So with that, we would have that positive x is less than a 3 or a negative x is less than 3. But here's what happens when we divide off the negative. In the negative case, it actually causes the inequality symbol to flip. And so that's an algebraic argument for getting that this sign needs to be a greater than. Essentially, in the negative case, it's like we've taken that negative value that's inside the absolute value and either multiplied or divided it to clear it off. So it'd be just an x on the left side, which gets the negative on the right side, but because it's an inequality, it's also going to cause that inequality symbol to flip. Alright, so we saw it conceptually why it needs to be a greater than, and we saw it more algebraically why it needs to be a greater than. The bottom line is when you split an absolute value inequality into its two equations, two inequalities, the negative case symbol, the inequality symbol is going to need to flip. Alright, so again, when you split an absolute value inequality into the positive case and the negative case, you're going to need to flip the inequality symbol for the negative case, and that needs to happen right away as soon as you split it. That's not something you can fix in the end. It has to happen right away. Well, that's the first nuance with the absolute value that make it more complicated with inequalities than with equations, is what to do with these signs, with the inequality sign. The other question is our conjunction. Is it an and or is it an or? And it has to be one or the other. With an equation, it's always an or, so we don't really hammer any notion home with that. It's just always an or. We keep everything we come up with. But with inequalities, sometimes it's going to be an and sometimes it's going to be an or, and we need to talk about which one that'll be. And again, I'm going to use our number line that we've developed. We already know what our solution set for this inequality looks like, so we're going to use that to kind of argue ourselves into an and or an or. Okay, so what I'm going to do is I'm going to graph each one of these inequalities that we have on separate number lines. So for the first one, we have that x is less than 3. So that would look like this, and it would just keep on going past the negative 3. Negative 3 isn't even a part of the question if we're just looking at that. Now, for the negative 3, we have x is greater than negative 3, so we gotta go in that direction. Now, I know what I'm aiming for. I want it to look like this. So that basically means down. And the reason I want to go, I need to emphasize the reason. The reason why I want it to look like that is because the absolute value is a statement of distance from 0. So we're looking for all x's that are less than 3 units from 0. And that induces this graph. That's a picture of everything that's less than 3 units from 0 in the negative direction and the positive direction. So I know that my graph needs to look like that. Now, when I take these two graphs down here into consideration, to make this graph up here, I'm going to be looking at where the graphs overlap or where they intersect. We don't want this piece, we don't want this piece, we just want where we have both of them. Well, which one of our conjunctions looks at the overlap, or just when they are both true? That's going to be the and, not the or. The and is what will give us distance from 0. Within between, it'll give us this 3 units distance from 0. And so when we split this, it's going to need to be an and conjunction that we're using while we solve it down. Because we want stuff to be close to 0. Think about it this way. If I have a less than, I'm wanting stuff close to 0. The distance it is from 0. Alright, so when we split a less than, this is going to be in general for less than. I want the distance that this stuff is from 0, so it needs to be close to 0. So we're looking at all the stuff within a certain radius of 0. Now, when we get to more complicated ones, it won't always be a distance from 0. It might be a distance from 3 because more is going on inside of the inequality. But it's always a distance, a radius away from some point. So hopefully that's starting to make sense, and you're seeing how conceptually, if we're talking about the distance from 0, we need to use an and so that we get the intersection or the overlap of the two individual graphs. But just to help hammer home what is going on, I'm going to contrast it with a greater than issue. So let us consider the exact same inequality, x, but this time it'll be greater than 3. Alright, so conceptually speaking, when we're talking about distance from 0, when we want it to be greater than 3, we want the distance from 0 to be greater than 3. That would be this stuff out here, and that would be this stuff out here. That's where stuff is more than 3 units away from 0. Less than, we're wanting it within 3 units of 0. Greater than, we're wanting it outside of 3 units from 0. Then if I split my inequality into my positive case, I'm going to have that x is greater than 3. My negative case will be x is less than a negative 3. Because remember, when we split to the negative case, we have to flip the inequality symbol. That's just going to be true across the board for the same reasons we've already argued. So the question that we're addressing now is this and or question. Is it an and or is it an or? Well, let me draw out the individual graphs. The graph for the first one is saying that x is bigger than 3, so we would go bigger than 3 on our number line. The graph for the second one is saying x is smaller than a negative 3, so we would go smaller than that. And again, we already know we want our graphs to combine to look like this guy. Well, if I chose an and, again, and is saying where are they both true? Well, they are not both true anywhere. And so if it were an and, our answer would be no solution or the empty set. It's only with an or, that's not what we want. It's only with an or. An or is anywhere, it's the union of anywhere that it is true. So the or, we would keep everything. It combines to give us the graph we're aiming for. I really like you guys to understand why things are the way they are, and so that's why I've been explaining everything I've been explaining so far. But the general rule is if my inequality, once my absolute value piece is by itself, if my inequality is a less than, my conjunction on my positive and negative cases is going to be an and. If once my absolute value piece is by itself, if it's a greater than, then my conjunction when I split it into the positive and negative cases is going to be an or. I don't try to memorize this. I just think of it conceptually. A less than is wanting me to consider the distance within a certain range, which gives me this type of solution set. A greater than is wanting me to consider the distance outside of a certain range, when is the distance greater than these things, and that's going to give me a solution set that's configured like this. It has to. So that's kind of how I use the concept to argue myself into what the conjunctions are and what the graph should look like. I find that if you just try to memorize it blindly, it's easy to get it backwards. Now that we've seen these two nuances. One, when we split into the positive and negative case, you have to flip the inequality symbol for the negative case. And two, when to choose an and conjunction and when to choose an or conjunction. Now that we have those two complexities under our belt, let's look at solving a more complicated absolute value inequality. Alright, so here we have our absolute value inequality. Negative 2 times the absolute value of x plus 3 minus 5 is less than or equal to negative 7. Now with these guys, just like we saw with the equations, before we split into our positive case and our negative case, we first need to isolate the absolute value piece, or get the absolute value by itself on one side of the equation. To do that in this case, I need to start by adding 5 to both sides of the equation. Alright, and then once I do that, I need to next divide both sides by the negative 2 coefficient in front of the absolute value piece. Again, I'm just trying to get the absolute value piece by itself. In this case, since when I divided, I was dividing by a negative 2 on both sides, it causes my inequality symbol to flip. This is very significant because remember, whether or not we're talking about a less than or a greater than scenario completely changes how we process our solution. In the beginning, I had a less than. I don't make my decisions based on the inequality symbol I had in the beginning. I make my decisions based on the inequality symbol I have once I get the absolute value piece by itself. So with that in mind, now we're ready to split it into the positive case and the negative case. The positive case is always going to be exactly what we have, but without the absolute value bars. In the negative case, we're going to make one side of the inequality negative. It's usually simplest to make it the constant side. And then we also, as we talked about earlier, flip our inequality symbol for this case. Next, we need to decide what conjunction is going to go with these. Now, our inequality symbol is an or, so we are is a greater than, and so we are looking for an or because we want to know when x plus 3 is outside of a distance of 1. So when is x plus 3 further than a unit of 1 away? Okay, now that we have our conjunction sorted out, we have our absolute value signs facing in the right direction, we will just solve each one of these down for x like we would with the compound inequalities we worked with before. That gives us that x is greater than or equal to a negative 2, or x is less than or equal to a negative 4. So with that, what we want to do next is go ahead and graph these. I'm going to do, the directions don't say to graph, but I'm going to do 2 separate graphs so we can see what's going on and continue to talk about the concept of how it all comes together. Okay, so there are 2 graphs, and it should, if you're tracking what's going on here as far as what absolute value means, this should be good as far as expectation, because we're looking for the distance something is like further out from something. It has to be outside of this distance. Alright, it's hard to conceptualize because we're not centered at 0 anymore because there's an expression inside the absolute value instead of just an x, but it's still the distance away from something. It's just our 0 has been shifted. In particular, our 0 has been shifted by 3, and it's going to be a negative 3 because of the minus 3 issue there. I'll explain that further when we get to graphing on 2-dimensional planes, but essentially this is, we need to be outside of 1 unit from a negative 3. So that all the graphs are within that concept are what we expect, but if you just follow the rule, once you decide the correct conjunction, if you just follow the rule, you know to put these together by putting everything together, because or keeps everything. So when we put all that together, our solution to that's going to be the interval from negative infinity to negative 4 inclusive, union negative 2 inclusive to infinity. Hopefully you can see why that is, because if we're talking about the distance something is, the greater distance something is 1 unit from negative 3. That's what all this is saying. Hopefully it's making sense to you. Some students try to just memorize it, that they have to flip the inequality, and less than is going to give them an and a greater than symbol will give them an or. And if that's the route you want to take, I'll never know the difference, but I like to have a concept to debate myself with when I'm struggling, and so that's why I like to explain it based on a distance within or a distance greater than or further than the value you're given. Go ahead and give some of these a try and see how you fare.